Hello, jumpre. Welcome back to another episode of Maths. This might actually be on Cool Computer Scientist. I don't know. Or care. It's time for Contextualised. Oh my goodness. It's been 2 weeks. I was meant to start the next episode sooner, but hey, things happen. So, got like a set of things we could look at. Could look at some chemistry, maybe. Could look at some formalised, or we could do. So I'll continue what we did last session, which I was going to say last week or yesterday, but it's neither. It was 2 weeks ago. I got my fingers open here. So essentially we looked at the fundamentals of maths, and we looked at how maths really fundamentally consists of objects, and we looked at what maths is, and we stated that some of the most common objects you'll see in maths, we've got graphs, you've got numbers, or complex numbers, or the more general form of numbers. There's two more things. Oh, how could I forget? Matrix numbers, which is the study interest of linear algebra. And then we also have sets. And essentially, it's kind of experimental. Every session I do is a bit experimental, but last week I sort of like knew what I was going to say and just went for it. This time I'm kind of planning to like improvise. I haven't tested out a section of this that I should have tested out. I wasn't thinking straight. Essentially, I'm thinking I should just like stick with order. I'll like cover whichever area I want to. I'll start with graphs maybe, because graphs are pretty sick. Okay, so you have an idea of what they sort of look like. This is getting in the way, that's fine. Just branch off. So we had a look at what they look like, but I don't think I talked too much about their technicalities. So for a graph, for any graph you can, I like to call it like an order, and its order is how many nodes it has. So this would be like an order 4 graph maybe. I don't know how common it is to do that. But this corresponds to a matrix number which would have the same order. So yeah, I'd say that's a pretty decent way to think about it. So we've got an order 4 graph there. If we had another node, it would be order 5. So the first characteristic of the graph is how many nodes does it have. And once you have the nodes, you do what I sort of like to think about in the corner, sort of feels that way when you look at the matrix equivalent of it. It's called configuring the graph, which is where you add the relations. So for example, let's say we had an order 4 graph. Okay, we've got 4 nodes. And now to make it a specific graph, you configure it by adding relations. And relations are such that every relation has to go from a node on the graph to another node of that graph. So you could do this. So we're going from a node on the graph to a node of the graph, which can be the same node. We actually call it a loop where it goes back on itself. And essentially by adding relations between nodes, you can configure the graph in that you make it a specific graph of that order. So here that's a specific order 4 graph. Okay. That's graphs. The bit where it gets pretty fun is where you switch it between matrix numbers and graphs. Essentially any graph can be re-represented as a matrix number. But we haven't done matrix numbers yet, so maybe we should do that. I really like matrix numbers though. Gosh, I only have 7 minutes, this is so sad. We could look at complex numbers, I might do that. When doing regular algebra, grab everything. When you do regular algebra, so say we do x squared minus 17 equals 0 or whatever, we tend to use the variable x for real numbers. When you're dealing with complex numbers, for one reason or another, we tend to use the symbol z. I guess one reason we do that is we tend to think about the components of a complex number as being, we usually get them variable numbers, variable letters x and y. So I guess just to keep things, it can be any letter, you could use w, h, d, doesn't really matter. But what does matter is that a complex number has various forms, so you can either, that's the most common form really, the one which you can sort of think about the easiest probably. But it has other forms too, so you can put it in this form, called the polar form, or you could put it in the exponential form, like this. You don't need to worry about the different forms, this one's the most useful. And when it's in this form, also when it's in this form, if you evaluate it out, if you don't, it doesn't. It has 2 components. We have names for these both components, so we call this RE of z, and we call this IM of z, for real and imaginary. And because we call it imaginary, this is where all confusion comes, that complex numbers aren't real. And while they're not real numbers, in the sense that they don't fit on the real number line from, say, 0 up to the positive numbers this way, or the negative numbers this way, it is a real number and it exists, and we could talk about why I defend that, but really I should get like an argument partner who disagrees with me, and we could argue why I would argue complex numbers do exist, even if they're not on the real number line, so therefore not technically real, as mathematicians call those numbers. Okay, so what the heck is going on here is the important question. The important thing going on here is, what is I? Because if I was, say, a real number, so let's say I was, say, 7, we could obviously combine the two. So if it was z equals 8 plus 7i, hello, by I, it's 3, so yeah, we just combine it. No, that's not how we do addition. 21 plus 8. Oh no, it is 28. No, it's 29. Being done. So yeah, so obviously I can't be some real number, otherwise they combine. So what is I? Most people define I by just saying I equals the square root of -1. And that works, but the thing is it's not complete. You can use that definition, it'll always work. But I sort of want to show why it doesn't have to be the only definition used. Let's do the power set of I. There's a lot of content here. Matrix numbers are cool. I can't wait to get into this another time. Alright, where should I put power set of I? Let's do it over here. So, I to the power 1, which is I, equals I. I squared, because I you could define as that. We can square that out pretty easily, because it's square root of -1. So I squared just gives -1, and regardless of how you define I squared with -1. It's like things that are true about it. Here we can see that's I minus I, because we can split into I and I squared, which will give us -1 times the I minus I. And then I4, the I will times by the I to make -1 times 1 equals 1. But this continues, so it essentially loops back around. So now if we do I to the 5th, well, we've got I to the 4, 1 times another I, to get I again. So therefore, I to the power of 6 is also equal to -1 because it loops back around. And this will repeat, so it's got a period of 4, so every 4 times it will go back around. So that means while we could take the square root of -1 to get I, we could also take the 6th root of -1. So this is alternatively, so I equals -1 to the half power, that's the square root, or it's equal to, no, square root, or it's equal to sixth root, or we can add another one, so we say -1 to the power of the 10th root, and in general it's equal to -1 times by 1 over 2 plus, no, 4n minus 2, where n is of the set of naturals. We haven't spoken about what the set of naturals is, so if you don't know what that is, then we'll do that another time, hopefully. Does that work? Yeah. So this is I would say this is a more robust and proper definition of I, but we don't tend to see it so much. Everyone just defines it as a root of -1.
I got you. Oh, you, man.
It is me.
Yo!